Welcome to part 3 of this FPGA development board tutorial series. In this video, we will work through a simple but important digital logic example, the realization of a NOT gate using the FPGA. We'll begin by writing the Verilog code for the NOT gate and then move on to synthesis and pin assignment using the Affinity design software. After that, we'll generate the required configuration file and program the platform flash. Finally, we'll demonstrate the design on actual hardware, where a change in the input signal results in the corresponding inverted output being observed using an LED. This example helps build a strong foundation for understanding how basic logic functions are implemented, synthesized, and verified on an FPGA. We begin by creating a new project in Affinity. A suitable project name, set as example, and a project location are selected. The FPGA family is set to Trion, with the device T20Q144, and the timing model I4. The top module name is set to top. Once the project is created, a new Verilog source file is added to the project. The file is named main.v, and it will contain the Verilog code for the NOT gate, where the output is the logical inversion of the input signal. The Verilog code shown here implements a simple NOT gate, also known as an inverter. The first line specifies the timescale directive, which sets the simulation time unit to 1 nanosecond and the time precision to 1 picosecond. This is mainly used during simulation and does not affect the actual hardware behavior. The module is named top, and it has two ports, A and Y. The signal A is declared as an input, and Y is declared as an output. Both signals are of type wire, since this design uses continuous assignment rather than sequential logic. The core functionality of the NOT gate is implemented using a continuous assignment statement. The statement assign y equals NOT A means that the output y is always the logical complement of the input A. When the input A is logic 0, the output y becomes logic 1. When the input A is logic 1, the output y becomes logic 0. This behavior directly matches the truth table of a NOT gate. Since there are no clocked elements or registers in this design, the output responds immediately to any change in the input. This simple example demonstrates the basic structure of a Verilog module, the use of continuous assignments, and the implementation of a fundamental digital logic function using an FPGA. After entering the code, we click on the Analyze button to check for any syntax errors. The analysis completes successfully, confirming that the Verilog code is syntactically correct. Next, we move on to pin assignment using the Interface Designer tool. Inside the designer, we first create the input signal, named A, and configure it as a GPIO input with a 3.3V I/O standard. For this input, we enable the weak pull-up option. This ensures that if the input pin is left unconnected or open, it will be read as a logic high, providing a defined and stable input state. The input signal A is then assigned to FPGA package pin number 18, as per the schematic. Next, we create the output signal, named Y, and configure it as a GPIO output. The output Y is assigned to FPGA package pin number 33, which is connected to the lead on the board. Once all the pin assignments are completed, the design is saved. The next step is synthesis and implementation. We click on the synthesis tool icon, and Affinity begins synthesizing the design and generating the required output files. After successful completion, the tool generates the .hex and .bit files. Since the FPGA configuration is stored in platform flash, these files must be converted into .bin format. To do this, we open the Programmer tool in Affinity, load the generated .hex file, and export it as a .bin file. This .bin file is the final programming file used for platform flash programming. With this, the design is ready to be downloaded to the hardware and tested in the next step. Let us now go through the steps involved in programming the platform flash using the CH341 programmer. First, configure the board for flash programming mode. To do this, short jumper J7 to place the CH341 in programming mode, and short jumper J2 to hold the FPGA in the reset condition. These jumper settings must be done before powering up the board. Once the jumpers are set, connect the development board to the USB port of the PC. Next, open the CH341 programming software on the computer. After the software opens, click on the Detect button. If the hardware connection is correct, the software will automatically read and display the manufacturer name, flash device name, and memory capacity of the platform flash. This confirms that the CH341 programmer is communicating correctly with the flash memory. Now, load the FPGA configuration file by opening the .bin file generated from the Efinix software. Once the file is loaded, go to the Operate section and enable the Auto Program option. Make sure that the options for Erase, Blank Check, Program, and Verify are all selected. Then click on the Auto button to start the programming process. The software will first erase the flash memory, then program the new data, and finally verify the written contents. After the programming process completes successfully, close the CH341 software. Now, remove the short on jumper J2 to release the FPGA from reset. Now the FPGA will automatically load the configuration from the platform flash, and the programmed design will begin running on the hardware. Let us now observe the hardware behavior of the NOT gate on the FPGA. In this setup, FPGA pin number 18 is used as the input, and FPGA pin number 33 is used as the output connected to an LED. First, leave pin 18 open. Since a weak pull-up is enabled, this applies a logic 1 at the input. Because this is a NOT gate, the output becomes logic 0, and the LED remains off. Next, short pin 18 to ground, which applies a logic 0 at the input. The NOT gate inverts this input, producing a logic 1 at the output on pin 33. As a result, the LED turns on. This simple demonstration clearly verifies the inverting behavior of the NOT gate, where the output is always the logical complement of the input. With this, we come to the end of part 3 of the FPGA development board tutorial series. In this video, we implemented a basic NOT gate, starting from Verilog code development, followed by syntax checking, pin assignment, synthesis, platform flash programming, and finally verification on actual hardware. By observing the LED behavior for different input conditions, we clearly demonstrated the inverting operation of the NOT gate using the FPGA. This experiment forms an important foundation for understanding how simple digital logic functions are realized and tested on programmable hardware. In part 4, we will move on to more advanced logic examples and experiments, building further on the concepts learned so far. Thank you for watching, and we'll continue with part 4 in the next video.